believe Professor Eager is doing the semester. If not, it's definitely available in the online series. This is a part that's very hard to inspect. There's a fuselage on one side, there's some transverse reinforcement inside the wing. So the best way to deal with this is to use the best possible material, so a drawn aluminum, and then you go and poke holes through it. The advantage is you know almost exactly what you're getting at off the factory in terms of fatigue performance. There are no grains from solidification and casting. The composition is all homogeneous. The little impurities are actually stretched in this direction through the process. If I had some precipitates, they all get elongated in that direction, and the crack was going this way. So when we look at this, it's very quick to come up to the conclusion that there wasn't as much of a support anymore to the system. So it started being loaded in bending when it was supposed to be tied to everything and just being loaded in tension and compression. Now you had bending in this particular transverse section, so that's the main reason why it started to crack. And you had bending because you just kept loosening you were losing rivets as you kept going on, popping out rivets because of outside loads that were out of plane. A lot of things that are hard to simulate with the computer, but you can look for it. There was an additional issue here where they were coming and making repairs. So they knew they had some rivets popping out, so they were coming back to put new rivets in. And it's always hard to line things up and make sure the load is still shared between all the rivets. So nothing terrible happened here, but they were definitely interested to know what we could tell them, but just by looking at it. Most aluminum alloys in aircrafts are strengthened to the maximum extent. And one of the main reasons for that is aluminum is so ductile but it's so soft that it makes sense to try to maximize the yield strain. It's going to allow you to use less material. But yield strain is not only important in tension, it's also important in compression for buckling. So for a lot of application, regardless of whether it's tension or compression, you want to increase your yield strength a lot. You can increase it by drawing in all these processes we talked about: recovery, recrystallization. You select your temperature, but then you're really, really losing on your strain hardening. So one of the best way to increase the strength of aluminum is precipitation hardening. And what happens, and these are different ways, by the way, that you can increase the strength. So if I just walk through this very quickly, this transformation is what we're going to talk about for aluminum. With aluminum, let's see. Good. We're done with this, clearly. Aluminum, there will be a temperature where you can have a lot of copper, magnesium, manganese that will fit into the solid aluminum. We're not talking about the liquid anymore. We just moved on. Now we started with a wrought product. It's been all processed. It's all the same composition. There would be in the solid phase this temperature. So I'll call it solid aluminum, so alpha phase. And this could be the concentration on a phase diagram of either copper, manganese, magnesium, manganese. There are a few of those that just really, really helpful in terms of increasing the strength by precipitation hardening. What happens here is, say I have, I'll put it 4%. It's close to the maximum. I put 4% copper. It's increasing my weight a little bit, but I'm willing to go with it. You go to this temperature, which is below the melting point. So if melting for aluminum is around 800 centigrade, we may be close to 500, something like that here. 600, I don't remember the exact number. But you put it in what we call in solution. So at this point, I have aluminum and copper sharing the same site in the crystal structure. So if I put it here, well, this is going to become very complicated. It's a face-centered cubic structure. At any location on the lattice, it could be any of those two alloys. Now, I'm lowering the temperature. So this, of course, it's a phase diagram with looking at the temperature here. As I decrease the temperature, I see that interface where now the equilibrium state is have two phases. One that becomes progressively purer, richer in aluminum, and the other one that's some form of combination of copper and aluminum and maybe other elements when you think about a real alloy that has more than two elements. So what you're trying to do is control how this transformation is going to take place to go from just one phase to a combination of phases. Typically, if you go very slowly, you'll form large precipitates at grain boundaries or other inclusions in the material, and nothing's going to happen. It's going to be sort of trying to put rocks in the river. They fall to the bottom, and it doesn't really prevent the flow of water in the river. If, on the other hand, what you do is you quench completely this point of homogeneous composition down to ambient temperature, you essentially supersaturate your structure with the copper, the magnesium, and the different alloying elements. Now you have a potential, because you're at such a low temperature, when there are some alloys that would actually form precipitates over time at ambient temperature, the 2000 series aluminum. So what people do to form these rivets is they quench it in ice, and they'll store everything. They store the rivets in the freezer, and then they take it off just before putting it in the machine, clamping it, because you get the biggest ductility if you haven't gone through forming any of those precipitates. All you have is the pure aluminum. You have the pure aluminum, you deform. It's a very high strain operation to take the rivet head and squash it. After that, just in the shop, at ambient temperature, you'll have the formation of those precipitates that I was talking about. So it's making use. You win both ways. You really reduce your yield strength and your hardening by not having any form of second phase into your structure, and by the time you're done, and the deformation of the rivets actually is also helping in forming these straightening precipitates after the fact. So there are a lot of technological applications of this phenomena. I'm trying to describe it to you from the physics of what's going on from the phase diagram, and I'm sure you can go on your own and find a lot of different application. We have stainless steels that we can do just about the same thing, precipitation hardened stainless steel, where you put everything in solution in a solid, quench it, and then you go back at a certain temperature, and that's what I'm going to describe to you to get to your hardening. Let's see here. Okay. I skipped a few slides because I think it's going to help with the flow here. So what happens after quenching, showing you a few options depending on the temperature that you go for reheating or precipitation hardening, aging. They're all the same. They just mean trying to slowly go closer to the equilibrium, where you take some of those alloying elements that you put in the same crystal, and now they're going to form a different phase. If you're at a low temperature, the exact details of that shape or precipitates that you're going to form is going to be different. At very low temperature, you don't have a lot of thermal excitation, you don't have much diffusion, so you're going to need to have a very small, stable nucleus. Very small and stable means that it's coherent. And I've shown some images. These are TM images, so you're looking only at 500 nanometers here. You're forming very, very, very fine precipitates in your structure, and you didn't create the interface. It's just a form of segregation. If it used to be the same composition everywhere, now all of a sudden you have a little more of it in this area, but it's still coherent with the base structure. as you keep increasing the temperature in this schematic here, you are able to form bigger and bigger nucleus. And you end up with a structure that has an interface with the aluminum. If it's a perfect interface, you lose the strengthening. You lose the strengthening because now the dislocation is just going to go around it. There's a nice transition with the dislocation. You created that grain boundary. At grain boundaries, dislocation can just come and go. There's a lot of flexibility. There's a lot of open space. So the real solution to this for strengthening is to be in between. You don't want to be perfectly, most of the time, you don't want to be perfectly included in the original lattice because the dislocation will go right through it. And you don't want to be completely separated as a rock that falls to the bottom of the river. You have to be somewhere in between where you create a strain field, and that's where the idea, that's where we're going to start to talking about dislocations a little bit more. I was able to form these precipitates that for now just say they're just exactly what I wanted. They're just exactly what I wanted because they're not too small so the dislocation just run right through it. They're not too big so the dislocation just goes around it. They form, so see this is the precipitate. They form a certain strain field. So here around the precipitate we call them semi-coherent because there is a certain strain. As in the whole volume there's an elastic strain, a deformation of the crystal surrounding that new face that we created. So these are copper rich precipitate. Around them we have a volume that's affected. So when I come here, dislocation, by the way, it's just a line defect that's moving in the crystal. As the line defects comes in, say all the way to this point, it starts to feel it. It's harder to move in those areas because of the strain. So what it tries to do is it will continue in the same direction because the direction is based on the driving force in shear, but it will not penetrate easily in these zones. And eventually it may get stretched to a point, and I'm going to try to make a sequential image of the same here. So if I exaggerate this, I think you soon get to see where I'm going. These two can recombine, and now you're left with a dislocation around your precipitate. And the dislocation keeps going. So the next step after this is you merge here, and now you have your dislocation is continuing to go, and you're left with a dislocation all around your crystal. Now the implication of this is yes, there's dislocation multiplication. This is starting to look actually bigger than it was originally without the extra defect around it. So an advantage of this type of hardening, and what you guys to keep in mind is it not only affects the initial point where say the crystal was relatively clean and I came with the first one. As you go, it becomes harder and harder to go through the precipitates, and that means a lot of hardening. If the precipitates are very fine, like I have here in this micrograph, the dislocations keep going right through it. From one time to the other, it's the same resistance. It's the same applies to what we call solid solution hardening. So solid solution, manganese is a good example. We had our crystal here. I just say, oh, I got some manganese here. Sure, it does have this little strain field associated with it in the crystal, but the dislocation in the end was just going to go right through it. And it will provide some resistance, but it's the same resistance whether you're going to your first percent of plastic deformation or whether this is the 20th percent of plastic deformation. So one of the technological advantage here is really how you go around and are left with more barriers after the fact. So that will conclude today, and we'll pick it up tomorrow. continue to talk about heat treatment, I need to tell you about steel. And I had a good example that's going to be next class about what happens when you try to make these things. Somebody asked me a question about casting of die casting. It's not sand casting. If you try to make an engine, like the fancy engines, they're die cast. And that's why they do this. You get a fine structure.
Some of them are still the sand cast.
Well, the valve covers are sand cast. I know that.
But like, if you go online, you can see a video of them casting the engine for a new Ferrari.
Okay. Well, the base process, the way they started it was with die casting, and I would definitely do that. I'd be reluctant to do a sand cast, but I believe you.